We present ReSpace, a novel framework for text-driven 3D indoor scene synthesis and editing with preference alignment. Scene synthesis and editing has emerged as a promising direction in computer graphics, focusing on the automatic placement of objects in 3D space to create realistic indoor environments. This has a variety of applications, including virtual reality, interior design, and robotics. Let me show you how our method works. ReSpace learns to add objects autoregressively into 3D indoor scenes via text-driven commands. Starting from an empty or partially furnished room, we can incrementally place objects one by one. While this visualization shows object addition, our framework also supports object removal and swapping, all controlled through text commands. First, let's look at the limitations of existing approaches. Current methods for 3D scene synthesis often represent object semantics using simple one-hot class labels, which lack rich descriptive information. Many ignore room boundaries entirely, support only rectangular ones, or rely on fixed-resolution floor plan renderings that fail on complex geometries. For editing, others require masked diffusion with manual intervention. LLM-based approaches often depend on weak spatial reasoning from general-purpose models not trained for 3D placement. ReSpace addresses these challenges through specialized language modeling designed specifically for 3D scene understanding. Our framework supports 3 core editing operations through natural language. We can add new objects to existing scenes, remove specific furniture pieces, and swap objects by combining removal and addition commands. Thus, unlike previous trained methods that use simple class labels, we can address objects with richer explicit semantics like modern or wooden chair. Our approach further handles complex room geometries through explicit boundary representation, uses a specialized model trained specifically for spatial reasoning, and supports editing operations via natural language instructions. So how does this work technically? At the heart of our approach is the Structured Scene Representation, or SSR, which encodes scenes as lightweight JSON objects with explicit room boundaries and natural language object descriptions. This allows to represent more complex, non-rectangular floor plan geometries as well. Now, given an object prompt, we feed both the existing SSR and the prompt into our specialized SGLLM, which predicts the properties of the next object to add. The model outputs remain in text form until we use our stochastic asset sampling engine, which selects 3D meshes based on both geometric constraints from bounding box sizes and semantic similarity using SIGLIP embeddings. We can repeat this process to add multiple objects autoregressively. For object removal, we use a zero-shot LLM to directly edit the SSR text, and for full scene synthesis, the same zero-shot model generates lists of object prompts. We further propose a voxelization-based loss, or VBL, as a novel metric for layout violations, providing fine-grained evaluation of object placement. Let me walk you through this visualization. We start with explicit room boundaries, shown as red cubes. We then show objects as blue bounding boxes before we sample corresponding 3D assets. Each object is voxelized to capture detailed geometric interactions. The VBL identifies 2 types of violations, defined simply as their sum: out-of-bounds voxels, or OOB, shown in red, and mesh boundary loss, or MBL, between objects shown in purple. These 2 metrics capture realistic spatial relationships that simple bounding box metrics miss, such as chairs positioned partially under tables. For training our SGLM, we employ a dual-stage pipeline combining supervised fine-tuning, or SFT, with group relative policy optimization, or GRPO. Our reward function considers both geometric and semantic constraints while trying to achieve 0 VBL. We use a positive-only distillation recipe that masks out samples with valid JSONs but poor quality, preventing reward hacking and preserving SFT behavior. Now let's look at some experimental results. We conducted comprehensive experiments on both single object addition and removal instructions, as well as full scene synthesis tasks. For full details, please refer to our main paper. In the following, we show a few qualitative samples. First, we show the ability to follow single object placement instructions. The blinking objects show the furniture being added with the corresponding text prompts displayed. Our method surpasses state-of-the-art performance on single object addition tasks, significantly outperforming existing baselines. For full scene synthesis, we generate complete room layouts from empty floor plans. The object prompts shown here were automatically generated by our zero-shot LLM, which creates appropriate furniture lists based on room type and size. Our autoregressive approach builds scenes incrementally, achieving competitive results compared to end-to-end trained baselines. We can further improve scene quality through test-time compute scaling using best-of-n sampling. Here we show scenes generated with n equals 8, where we sample multiple candidates for each object addition and select the best one based on semantic and geometric criteria. This approach allows us to surpass baselines on full scene synthesis as well, while maintaining the flexibility of our autoregressive framework. Finally, our stochastic asset sampling provides additional flexibility by moving beyond greedy selection. Starting with a predicted bounding box, we can sample from a distribution of compatible assets that match both the geometric constraints and semantic description. This enables diverse furniture choices while maintaining appropriate sizing and style consistency. The parameters of the distribution can be tweaked during scene completion and editing, allowing for flexible asset selection during inference. In summary, ReSpace demonstrates how specialized trained language models can effectively handle 3D spatial reasoning for indoor scene synthesis and editing, opening new possibilities for intuitive scene manipulation via text-driven representations and interactions. Thank you for watching.